Hello, this is the section 5.7 lesson. In this section we're going to talk about a hypothesis test called the goodness of fit test. In this hypothesis test we're not going to be testing a claim about a population parameter like a population mean or variance or proportion. Instead we're going to be testing a claim about the distribution of a random variable. Now the theory of this test is based on the chi-square distribution. So let's briefly review the chi-square distribution. A random variable with a chi-square distribution has only non-negative values. And there are different degrees of freedom of this type of distribution. Here in this graph we graph some different density curves for different degrees of freedom. So here's the n equal 3 density curve, the n equal 5 or the 5 degrees of freedom density curve, and here's the 9 degrees of freedom. Notice that they kind of have a bell curve shape, but they're kind of skewed in one direction and they only have non-negative values. So a random variable with a chi-square distribution is denoted by this notation, chi-squared of n, where n denotes the number of degrees of freedom. Now associated with the chi-squared distribution are critical values. And so the definition, let's let p be a number between 0 and 1, and x be a random variable with a chi-squared distribution with n degrees of freedom. So our critical value, denoted chi-squared sub p of n, is a positive number such that the probability that x is less than the critical value is 1 minus p. And this figure here illustrates this definition. Here's our chi-square density curve with n degrees of freedom. Here's our critical value. The area to the left is 1 minus p, and the area to the right is p. So we're going to use critical values of the chi-squared distribution in this goodness of fit test. The critical values are given in table C4 from the appendix. Across the top, if we have different values of p, that's the subscript, and then on the left we have the number of degrees of freedom. The degrees of freedom here are denoted r instead of n, and here in our examples you'll see why we denote those r instead of n. So the critical values are given in the middle. Again, this is a table of critical values. This does not give us areas underneath the chi-square density curve directly. So to illustrate this goodness of fit test, let's look at this example. A student simulated dandelions in a lawn by randomly placing 300 dots on a piece of paper with an area of 100 square inches. He then randomly chose 75 different 1 square inch sections of paper and counted the number of dots in each section. And so here's the data that we record. In 4 different sections we had 0 dots. In 15 sections we had 1 dot. In 14 sections we had 2 dots, and so on and so forth. So the number of dots ranged from 0 up to 8. Now let's let the random variable x denote the number of dots in a 1 square inch section. So it seems reasonable to claim that x has a Poisson distribution with parameter lambda equals 3. If we think back to chapter 2, a Poisson distribution dealt with describing the number of occurrences per interval. Here an occurrence is a dandelion or a dot, and an interval is a 1 square inch section. So it's reasonable to assume that x has a Poisson distribution. Now the parameter lambda was the average number of occurrences per interval. In this case we have a total of 300 dots and a total of 100 1-inch square sections, or a total of 100 square inches, and so lambda is 300 divided by 100, which is 3. So this seems reasonable. So we're going to use this goodness of fit test to test this claim. Okay. So let's define some terms here. So let's let p sub I equal the probability that x equals I, where I is a number between 0 and 6. And we're going to call this number p sub I the actual probability that x equals I. Now if the claim were true, meaning if x really did have a Poisson distribution with parameter lambda equals 3, then for instance the probability that x equals 1 is going to be equal to this. So this number comes from the probability mass function of a Poisson distribution. So here we've got lambda to the x divided by x factorial e to the negative lambda. If we do that arithmetic, that comes out to be 0.149. And so we're going to denote this number pi sub 1. Now pi here is not the number 3.14, it's just a Greek letter. So we're going to note this number pi sub 1, and this number we're going to call the claimed probability that x equals 1. So here p sub I is the actual probability, and pi sub 1 is the claimed probability. Okay. Now, if the claim were true, meaning if x really did have a Poisson distribution, then in 75 sections, as we selected, we would expect that about 14.9% of those sections would contain exactly one dot. So take 75 times 0.149, we get 11.2. So this is what I would expect if my claim really were true. So now we need to compare this expected value to our observed value and determine if they're significantly different. So that's the basic idea behind this goodness of fit test, and specifically it's called the chi-squared goodness of fit test. The purpose is to test the claim that a random variable x has some particular distribution. And there's several steps to it. First is we're going to divide the range of x into k categories. In this case, we're dividing it into 7 categories from 1 up to 6. And then from our data, we're going to observe values of x and record frequencies of the categories. We're going to denote those observed values O sub I. And then we're going to calculate expected frequencies of categories, denote those E sub I as we just did. And then step 4, we're going to calculate our test statistic. So this formula says we're going to take each observed value, subtract the corresponding expected value, square it, divide it by the expected value, and then we're going to add that up over all categories. And we're going to denote that test statistic with the letter C. Now, our critical value is going to come from the chi-squared distribution. Specifically, it's going to be chi-squared sub alpha of k with k minus 1 degrees of freedom. So we're going to take the number of categories, subtract 1, that's our degrees of freedom. And alpha is our significance level. The p-value is the area to the right of the test statistic under the chi-squared density curve with k minus 1 degrees of freedom. And then to come to our technical conclusion, we're going to compare the test statistic C to the critical value. If the test statistic is greater than the critical value, or the p-value is less than alpha, then we're going to reject the claim that x has the claimed distribution. The requirements for this type of test are number 1, that the data have been randomly chosen, and then number 2, each expected frequency is at least 5. This is going to be an important requirement, as we'll see come up in our next example. Okay. So going back to our previous example, here we've got this table that illustrates the number of categories. Here we're going from 0 up to 6. And then right here are our claimed probabilities. And these are calculated using the Poisson PMF. Here's the one claimed probability pi sub 1 that we already calculated. This number pi sub 0 can be calculated in the same way. I would just replace 1 with 0, and the others are calculated similarly. Here's our observed values from our data, and then here's our expected values. Those are calculated by simply taking the claimed probabilities times 75. And then here we show the calculations of our test statistic, each observed value minus the expected squared divided by the expected, and then we add them up, and then here's our test statistic. Now, let's formally state our hypotheses that we're testing here. The null hypothesis is the statement that P0, that's the actual probability of 0 dots, is equal to the claimed probability of 0.05. And P1, the actual probability of getting exactly 1 dot, equals 0.49, the claimed probability. And then P2, P3 up to P6 is equal to this. So the hypotheses, the null hypotheses, is really a collection of 7 inequalities in this case. And then the alternative hypothesis is that at least one probability is not as claimed. Maybe one is different, maybe all 7 are different, maybe 2 are different, I don't know. But at least one is not as claimed. That's the alternative hypothesis. Okay. And so our critical value in this case, we'll use a 0.05 significance level. We have 7 categories, so 6 degrees of freedom. And if we look up that critical value, we get 12.59. And so our test statistic 2.23 is much less than this critical value, and so the technical conclusion is that we do not reject the null hypothesis. The null hypothesis is really the same as the claim that the random variable has a Poisson distribution with lambda equals 3. And so the final conclusion in non-technical terms is that it is reasonable to assume that x has a Poisson distribution with parameter lambda equals 3. So that's the basics of using the chi-squared goodness of fit test.